Okay, so we're going to take a look at something called relative vectors. Now, we're going to go through this kind of quickly. I could give it a bit more thorough of an approach, but I want to try and make certain that this is a smaller segment so we don't get bogged down in it. This is something that I've been kind of weak in some of my classes. It shows up from time to time on the AP exam. It's useful, certainly, but it's not something that is really core to it, and so a lot of times I'll kind of skip over this. On the APC exam, for instance, there's usually maybe one, maybe two multiple choice questions that show up maybe every year, every other year or so. It's not something that is a key part of something that you desperately need to know, but it does actually bring in some ideas that I could spend a little bit more time on, but I won't. Big thing that I want to talk about with this, introducing it, is something called reference frames. Now, reference frames is a term that I'll throw around some, and on the front of the AP Physics exam, they actually say some special terminology that says all reference frames can be assumed to be inertial reference frames. That's a little bit of housekeeping that refers to mainly theory of relativity stuff, and it basically means that physics works the way that we expect it to work. Non-inertial reference frames are technically accelerating reference frames, and we'll talk a little bit about that. But it's something where sometimes the laws of physics can get a little weird compared to how we learn them the first way. They just get a little more complex in their application. In short, nothing in my classes is ever going to be at least incorporating the ideas of non-inertial reference frames, because so far as I know, we don't go into that level of detail in general relativity, if we even talk about that. Or, sorry, special relativity, I think, is where that kicks in initially, and then it carries over to general relativity. But the idea of reference frames is actually a fundamental thing that begins to deal with relative vectors. In short, relative vectors are based off of something called reference frames. And reference frames are basically where you are, where you're setting up your coordinate system. In fact, reference frames are heavily geared around the idea of your coordinate system and where and how you are setting that up. So for example, my reference frame right now, and what we normally use in the context of our classes, is in the classroom. So I'm going to stand right here, and I'm going to ask you the following question. How fast am I moving? Well, the answer to that actually depends on our reference frame. If my reference frame is the usual reference frame, then that means that I've set up my coordinate system around my classroom, and this could be the origin. And I stay right here at the origin, and I don't move. I just sit right here. So my motion is 0. How fast am I going? I'm going 0 miles per hour, or 0 meters per second. But that's if my reference frame is the classroom. Now, I want you to stop and think about this for just a moment, because if I ask you how fast I'm going, you're likely to say, well, you're going 0. Your reference frame right now is that camera, and that camera's reference frame is technically also the classroom. But if I were to knock over that camera, as it fell over, I could stand completely still, and you would see me move to the other side of the screen. That would be motion from your reference frame. You're seeing things from the camera's viewpoint. And if the camera moves, but you're moving along with it, it looks like everything else in the room moves instead. That's your reference frame. Now, if our reference frame is the classroom, as long as I'm not moving with respect to the classroom, in other words, I'm sitting here and the classroom is sitting here, then there's no motion. Same thing with the camera. I didn't knock it over. Neither it nor I are moving in our reference frame. So that's if my reference frame is the classroom. There are other reference frames. If I wanted to go off of the Earth, and I want to imagine, because remember, we're on the Earth, and is the Earth sitting still? No. Well, in one part, the Earth is spinning. That's how we get days. And if you stop and think about it, right now, if you are sitting in a chair and you continue to sit in that chair all day, when the Earth goes around, rotates one complete rotation, imagine that's behind it, but one complete rotation in a day, if you're sitting happily in a chair right here, then you go all the way around the Earth. You travel around the Earth, so to speak, every day. In fact, at the latitude that I'm at, that means that right now, me standing completely still on the surface of the Earth and the surface of the Earth spinning, if my reference frame were the space looking down on Earth, watching it spin underneath, then they would see me go flying by at about 400 meters per second. That's almost 800 miles per hour. That's pretty fast. That's really fast, honestly. That's, what, over Mach 2 at least? So that's twice the speed of sound. That's faster than pretty much any of the commercial jets are flying. And that's the fastest that most people actually get on a regular basis. You're going faster sitting in that chair than most planes do, but only from a given reference frame. As long as your reference frame is down here on Earth, well, that camera, yeah, it's also going about 800 miles per hour, moving the same as me, and that's why I don't appear to move, because we're both moving together. We are in the same reference frame. If I were in orbit looking down, I could watch everything fly by underneath, even if I were sitting absolutely stationary. And that's just one reference frame. Now, if I wanted to go to something outside the solar system, I could see that the Earth is not only spinning, but I could also see that it is going around the sun. So from the Earth frame of reference, let's see, from the classroom, I'm going 0 meters per second. From the Earth frame of reference, I'm doing something like 400 meters per second. That's circa 800 miles per hour. If we were looking at the Earth's orbital velocity as it goes around the sun, because space is really big, so if we did looking down on Earth's orbit, our reference frame would be something, say, outside the solar system, looking down on it from above, for instance. The Earth's orbital speed is about 30 kilometers per second. That comes up to approximately 67,000 miles per hour. That's how fast you are going sitting in that chair as you're riding on the Earth and the Earth goes whipping around the sun. It all depends on your reference frame. You wouldn't guess it based off of, well, I appear to be standing still, because both I and the camera are in the same reference frame. And this sets up the idea of these relative vectors. Now, you could go even further out. The sun orbits around the center of the galaxy at something like 200 kilometers per second, I think. Some of these speeds start getting so large that they boggle the human mind. But let's take it back from that a little bit, and let's talk about how reference frames deal with something that you're more likely to work with. I've got a few examples that we're going to work through so that you can get an idea of it and how to work with them. Let's say that you, that'll do, are in a car. And you're driving along, maybe in the back seat, with a leg, hip problem. Anyway, and someone else is driving so that the car keeps going, or it's self-driving, if you will, and you're driving down the highway. Now, you're driving down the highway probably at something like, the velocity of the car might be something like 60 miles per hour. Or as we found in class, that's about 26.8 meters per second. Great, so that's the velocity of the car. And since you are in the car, and the car is setting up your reference frame, you're moving at 26.8 meters per second. Now, the person in front of you is also moving at 26.8, and if you were to take a pen, and you had it in the car, while you're driving down the highway and you drop it, it's not like it immediately flies back and hits you in the face, because it is also in that same reference frame. It's moving forward as you hold it at 26.8 meters per second. You drop it, and it appears to fall straight down in your reference frame. From a viewer outside looking at the car, they have a velocity, we'll call this the velocity of the person, of 0 meters per second. You are in the car, and if you drop a pen, you see the pen from your viewpoint to have a velocity of 0. Well, at least in the x direction, I should say. It speeds up going down. So its y velocity becomes something very different. But you see it fall straight down. To someone watching from outside, though, the pen begins to fall and the car continues moving forward, and then the pen begins to fall. If you were to actually watch as the pen falls, it would do this. It would fall down but still be moving forward at the 26.8 meters per second. Why? Because it's in that reference frame, and that's how fast it was going to begin with. Now, if you hold it out the window, outside the window and you let go of it, it would appear to fall backwards because of air resistance. A force is going to apply on it, which will then change its motion some. But if you've got it in the car where it's nice and shielded from the wind, it is also moving at the same speed horizontally as you, and from your viewpoint, you drop it and it falls straight down. So it has a speed the same as the car, where we're going to say that the velocity of the marker, the pen that I have that I'm going to drop, has 0 meters per second in the frame of reference of the car, but it has the same velocity as this. From this person's viewpoint, they'd see the car and everything in it with a speed of 26.8 meters per second. And so we can find, let's see, we've got the velocity of the marker with respect to the car is 0 meters per second. And this is the notation that you usually see with these relative vectors. What we're doing is we've got direction, velocity is a vector, and they're relative to where you are looking at them. If you're in the car, pen drops straight down, doesn't move in the x at all. It has a speed of 0, or a velocity, I should say, of 0. If you're looking from outside the car, it's going to follow along with the car. You don't see it drop straight down. It actually drops down following along with the car. So you would not see it as a velocity of 0. What you would do is the velocity of the marker with respect to the car is 0 meters per second. If I wanted to, and I know that the velocity of the car with respect to the person or the ground is equal to 26.8 meters per second, I can actually combine these and find what the velocity of the marker with respect to the person or ground would be by doing the following. The velocity of the marker with respect to the person is going to be equal to the velocity of the marker with respect to the car plus the velocity of the car with respect to the person. Basically what happens is these two things group together and then they kind of annihilate each other, is a way of imagining it. What I'm doing is I'm finding the speed from one viewpoint, adding it to what that viewpoint is actually doing, and that will tell me what my speed is in another reference frame. Relative vectors are how you move from one reference frame to another. And so what you can do is you can add these together. So I'd have 0 meters per second. That's what we see for the marker, plus 26.8 meters per second for the car with respect to the ground. And so what the person on the ground would see the marker do would be 0 plus 26.8 meters per second, which is 26.8 meters per second. Another way of looking at this, let's go with some traffic. Let's say we've got a road like this. Now I've got a red car zooming along this way, and we'll say that the velocity of the red car with respect to the ground is, well, let's call it a highway. We're going to say that it's 26.8 meters per second. It's about 60 miles per hour. Let's say that we've got a blue car on the other side of the median going the opposite way. So I'm going to do velocity of the blue car with respect to the ground equals 26.8 meters per second. I suppose I should actually do negative because it's going to be, since it's a velocity, it's headed that way. Great. So one of the things that we learned in vectors is we can actually reverse a vector. This is the blue car with respect to the ground. We could actually switch this to be the ground with respect to the blue car. It all depends on what you want to set up from your frame of reference. Now, why I say that is this. If you've got someone standing on the ground, they're going to see the red car going positive 26.8, so 60 miles per hour that way, and they're going to see the blue car going 60 miles per hour that way, which is negative. Now, what I'd like to know is, from the frame of view, or the reference frame of the red car, when they look at the blue car, what do they see? Well, I'm going to have to work through the common thing that they have, which is the ground. So I can do the following. The velocity of the red car with respect to the ground is 26.8 meters per second, and the velocity of the blue car with respect to the ground is equal to negative 26.8 meters per second. Now, one of the things that we can do is we can actually reverse these. We can go, instead of the velocity from the ground's point of view, we could look at the red car. And if I'm in the red car and I look down at the ground, it looks like it's going that way at 26.8 meters per second. In short, I can reverse these reference frames by taking the negative. Negative RG, red car with respect to the ground, is equal to the ground with respect to the red car. So what that means is, from the red car's viewpoint, the ground is going 26.8 meters per second, 60 miles per hour, that way. If you're sitting in the car and you look down, you see the ground going the opposite direction from your viewpoint. Now, in reality, you know that the ground's sitting still, at least from the frame of reference you're used to, and you're going forward. But this is all about setting up what we look at. Because honestly, again, the ground's not actually sitting still. The Earth is spinning and going around the sun and so forth. Okay, now that I've got this, I find out that we can have the velocity of the ground with respect to the red car is going to be negative 26.8 meters per second. Now, here's what I want to do. I want to know what the blue car is doing from the red car's point of view. And that's why I've reversed this, so now I've got what's happening from the red car's frame of reference. I can find the velocity of the blue car from the view of the red. And I would define that vector as the velocity of the blue car with respect to the red car. And I could get that by doing the following. Well, I want to have the blue car over here, so I'd have the velocity of the blue car with respect to the ground, and then I would add that to the velocity of the ground with respect to the red car. Now, why did I use ground with respect to the red car and not red car with respect to the ground? Remember, our goal is to get these two to the same, so when we combine them, that actually cancels out, and we're left with the blue car with respect to the red car. That's why I did that reversal. And we know from just a moment ago that this is negative 26.8 meters per second plus the negative of the red car with respect to the ground, so that's minus 26.8 meters per second. And what we find is that the velocity of the blue car from the red car's point of view is that it is moving at negative whatever that's going to be. You can laugh at me all you want about the whole, can't I do this in my head? I probably can, but I don't want to get it wrong. So here we go. Negative 53.6 meters per second, or approximately 120 miles per hour go in the opposite direction. If you're sitting in the red car and you're looking at the blue car coming at you, from your point of view, it is flying at you at about 120 miles per hour. You're going 60 miles per hour this way, it's going 60 miles per hour this way, but from your viewpoint, you're watching it fly at you at 120 miles per hour. Here's how we work with relative vectors, and they allow us to change from one frame of reference or reference frame to another. All motion in the universe is relative. You don't know if you're moving unless you can see something outside your reference frame. Again, you sitting in your room right now, wherever you're at, if you look around you, your immediate response is you're not moving. And yet we know that the Earth is moving, it's rotating, it's going around the sun, and the sun is moving. We're moving a lot more than we would ever imagine just sitting still. We just don't see it because we operate in one reference frame. Doesn't mean the others are wrong, and it turns out that all of physics works as long as you keep track of your reference frames. Usually what we do is we set them up in the logical reference frame, in the classroom, or following whatever object or ground that our problem is set up with. Okay, so we talked a little bit about traffic. So here's one that can actually emphasize that. I want you to think about this. So let's say that I have a pitching machine. I'm going to have a pitching machine. And it pitches baseballs, or let's do tennis balls. And let's say that I set that tennis ball pitching machine to fire the tennis balls with a velocity of, since it's pointed this way, we'll point it left, we'll call that negative 30 meters per second. Okay? So that's about 70 miles per hour. Now, if I just sit the launcher on the ground, it has a relative speed to the ground of 0, and it will give a relative speed to the tennis ball from the launcher of negative 30 meters per second, and it goes flying off this way. But imagine this. Imagine I have a truck, a pickup truck. Not my best pickup truck drawing ever. Great. And what I'm going to do is I'm going to put that launcher in the back of the pickup truck, and I'm now going to say that the pickup truck is moving forward at 30 meters per second. Now, if I want to be ultra precise, then I would say that this is the velocity of the truck with respect to the ground. It is moving 30 meters per second to the right with respect to the ground, about 70 miles per hour. And if I've got my tennis ball launcher set to fire the ball at 70 miles per hour, whichever way it's pointed, and I point this backwards, then the ball launcher would actually have, let's see, with respect to the ground, it would fire this at, let's see, so ball and ground. Great. So if I wanted to do this, I'm going to fire it like this. What we can rapidly find is with the relative vectors, if the truck is moving forward at 30 meters per second, I don't think I've got this set up exactly the way that I want, but I want to keep this moving so you can get a pretty good idea of what we're doing with the relative vectors. And the pitching machine is going to fire it backwards at 70 miles per hour, and the whole thing is moving forwards at 70 miles per hour. What do you think is going to happen from the frame of reference of a person standing here? Well, the truck and the launcher are going to continue moving at 70 miles per hour, and this will have a relative speed to that, relative velocity of 70 miles per hour, and those two, when they add together, come up to 0. What you'll get is, as soon as the launcher actually fires it, the ball just falls straight down, as strange as that sounds. Hang on just a second. Okay, sorry about the cut there. My camera ran into some problems. I'm going to show something real quick in regards to what we were just talking about with the truck. So this is a Mythbusters episode where they're actually trying to set that up. They have a small cannon that actually fires a soccer ball. Let's see, so it fires, and what they're doing is they've set it up where the truck is going pretty much exactly the same speed that the cannon fires the soccer ball, and here it is in slow motion. I will link to this in the comments. I'm not trying to steal thunder from Mythbusters, but I wanted to show that here is a video that actually shows the exact thing that we're talking about. Instead of it going flying back the other way, because of how the relative vectors work out, it actually cancels out perfectly and the thing falls straight to the ground from the reference frame of the ground. Now, I'm going to move on to the next slide, and you will see that I was talking to myself alone in the room for a lot longer than I'd like to admit. So here's an example that I gave. Let's say that you are a pilot and you're leaving, let's say, from Dallas-Fort Worth Airport and going north to OKC. Now, it's probably not due north, but for this, we're going to simplify it and say we want to go due north to OKC. And let's say that we have a crosswind of 10 meters per second. That's about 20, 25 miles per hour, something like that. And so here's the thing. You're trying to go north, and the wind is blowing to the west, and what it will do is it will blow your plane off course, which is what this blue vector is supposed to represent. If you just aim at OKC and you try and just go straight towards it, the wind is going to blow you off course. And at some point, you're no longer looking at OKC, so you're going to have to go, well, I'll just keep looking at OKC, but the wind is still blowing you off course. What you'll end up with, under the best circumstance, is a path that looks a little something like this. That's still not ideal. It's especially not ideal if you go way out here and then try and correct and go over there. Not what you want to do. What we need is to be able to compensate for that wind so that we can go straight north. And so let's see, I'm going to get that out of the way. Here's what we want to do. Like I said, I've got a couple of things that are already filled in, but I'll take you through the important stuff. We have a speed. Let's say that the speed of the plane is, I forgot to mention that over here, about 250 meters per second. That should be a fairly realistic value. So we have a limited top speed of the plane of 250 meters per second. But we could then choose, we don't have to go straight north, we could aim to the west, or we could aim to the east. The idea behind this is we're going to aim a little bit to the east so that as we go this way and the wind blows us off course, well, not actually off course, blows us in a different direction than we are pointed, if we balance it just right, as we're trying to go this way, the wind will keep us going straight north. This is a very common place where you would need to deal with this. So if you were interested in aviation, especially doing things like navigation, you would need to be able to solve exactly this. So what you really need is the following. You need a vector with 250 meters per second. This is your plane, and you need an angle. You need to know which way to point so that you're not blown off course. And you know that there's another vector, the wind, which is 10 meters per second pointed to the west. So what you're actually looking for is this. We're going to add these two vectors together, and we want them to come up with this, our actual speed of the plane, or velocity, I should say. Our actual path will take us straight north. Now, in order to do that, what we're actually trying to do, you can see here that from drawing this out, my x component of my vector here needs to match this one so that they actually cancel each other out, and that relative result gives me only a velocity or speed, however you want to look at it, in the northward direction. So I've got a y component here and an x component here. If I know the hypotenuse here is 250 meters per second, and that I need a component in the x that is 10 meters per second to the right or to the east to counteract the 10 meters per second to the west, then I can go over here. This is the adjacent side. I can do cosine of theta as 10 meters per second divided by the hypotenuse, 250 meters per second. And I find that this is 87.7 degrees. So if you're the navigator, you quickly draw this out and you go, okay, pilot, I want you to point due north. And then we're going to turn a little bit by 2.3 degrees off to the east. And what's going to happen is, as you do that, you're going to try and go a little bit, you're going to go mostly north, a little bit to the east, and the wind is going to blow you to the west, and you will end up having a nice, straight, resultant vector that takes you straight north. This is, again, relative vectors. We're trying to get this vector and this vector to add together in a way that they can cancel each other out. So from the viewpoint of the ground, we end up with only a resultant in the y direction.